In this lecture, I would like to discuss about singularities, poles and residue. So, I will begin with the definition of a singularity. The definition of a singularity is a point z equal to a is called a singular point for a function fz if fz is not analytic at a. So a singular point is a point which is not analytic at that point. So z equal to a is not analytic at that point. It's called singular point. Now I just give an example. Fz is equal to z by z minus 1. So if you look at z minus 1, this is not, z minus 1 is 0, then z equal to 1 is a point, so which is not analytic at that point, hence z equal to 1 is a singular point. We say fz has a singularity at z equal to 1. I have the definition of isolated singularity. A point z equal to a is called an isolated singularity if z equal to a is the only singular point. It is the only singular point in the neighborhood mod z minus a less than delta, of course for each delta. So if in this neighborhood a is the only singular point and there is no other singular point except a, then it's called an isolated singularity. The same example I can give. So fz equal to z by z minus 1, z equal to 1 is an isolated singularity. Let us talk about the Lorentz series. Every function fz which is analytic can be represented as a power series, as a series of this type, z minus a whole power n equal to 0 to infinity plus summation bn z minus a whole power minus n runs from 0 to infinity. So every fz, of course provided mod z minus a is less than delta, the power series is valid only in the disk or in the neighborhood mod z minus a equal to less than delta. This is called, because this is n positive, is called analytic part. And this is very crucial for us for further discussions. It's called principal part. So principal part of fz, analytic part of fz. Now a very crucial definition for a pole. A point z equal to a. I am talking about a point a. A point z equal to a is a pole for the function fz if the principal part, I'll write down pp, the principal part fz is equal to summation n equal to 1 to infinity bn z minus a whole power minus a negative this is n negative. I mean n positive, so minus n will be negative. So Bn z minus a fz equal to Bn z minus a has finite number of terms. If it has a finite number of terms, then it's called a pole. Suppose the principal part contains infinite number of terms. If it contains infinite number of terms, then A is called essential singular or essential singularity for fz. So z equal to A is a pole if it contains finite number of terms, is it not? So what I have to do is, suppose I have z minus a, that means Bn not equal to 0, then A is a pole of order n. It's a pole of order n. That means the principal part of the Lorentz series Bn z minus a whole power minus n runs from 1 to infinity. If it's non-zero, then this has a pole of order n. If n equal to 1, then A is called a simple pole. Now, if I take n equal to 2, then it's called a double pole. Of course, if it is more than 1, it is called a multiple pole. Now, I will talk about the removable singularity. Removable singularity z equal to A is called removable. It's called removable if the limit of fz z tends to A exists. Then it's called removable singularity. And I can write a small example on this. Limit of sin z minus a by z minus a as z tends to a. This is fz. So I'm finding out the limit of fz sin z minus a by z minus a as z tends to a. This exists. This is 1, which is not 0, which is fz exists. Hence, z equal to a is a removable singularity. It's a removable singularity. You can find out many other examples of removable singularity, essential singularity, and a simple pole. Well, let us see another example of this function fz equal to z square minus 2z plus 3 over z minus 2. Now, 2 is a singular point. That means this function is not analytic at 2. Now, if you look at the zeros of fz, that means z minus 2, 0. This implies z equal to 2. So, z equal to 2 is a singular point. Now, also z equal to 2, which is finite, is a simple pole. I have this. At another example, which is z by z minus 2 whole cube. Here 0 sub f z, z minus 2 whole cube. So z equal to 2 is a singularity. Not only that, it is repeated. So z2, z minus 2 whole cube. So it's here I can say n or m, whatever, it doesn't matter any, it's a symbol. So m equal to 3 is, so z equal to 2 is a pole of order 3. It's a pole of order 3. It's more than, if it is 2, it's called double pole, simple pole, and pole of order 3. We can give many other examples, like consider this fz equal to a fantastic example, e power z by z. E power z by z. Simply you can see z equal to 0 is a simple pole. Z equal to 0 is a pole which is of order 1, so it is a simple pole. And you can test this simple remove whether it is they are removable singularity or not. Z equal to 2, whether it is a removable singularity, essential singularity. Just these are all certain examples which you can see. Then let us talk about the residue. So for that, let z equal to a be an isolated singularity. Then you can write down the Lorentz series fz equal to sigma an z minus a whole power n equal to 0 to infinity plus, I'll write down simply, I will change the letter bm, m runs from 1 to infinity, z minus a whole power minus m. The coefficient of z minus a whole power minus 1, which is 1 by z minus a. The coefficient of z minus a whole power m equal to 1 means it is b1, is called the residue of fz at a. Now, this also can be seen as follows. I mean, it's very difficult all the times to see the expansion and then evaluating the coefficient of 1 by z minus a. Always may not be feasible all the times. So I have another way of defining residue. So residue of fz z equal to a is 1 over 2 pi I integral of fz dz over c, where c is a closed curve and a is already given. It is an isolated singularity. So a is in or on c. It should lie in the C. Then we'll say residue of fz can be evaluated 1 over 2 pi I fz dz. Now, I have a remark. That means actually I can prove all these things, but I will make it as a remark to note certain things, how to calculate residue for different singularities, for different poles. Remark 1 is, suppose z equal to a is a simple pole, then I can evaluate the residue of fz z equal to a. I can evaluate this as limit z tending to a, z minus a fz. That's all. Simply evaluate that limit. That will be the residue of that. Suppose z equal to a has a multiple pole or a pole of order m, that means it has a pole of order m, then residue of fz z equal to a can be evaluated as the limit z tending to a. Of course, I have to write down, because it is a pole of order m, so I will write down the 1 by m minus 1 factorial limit z tending to a d power m minus 1 z by dz power m minus 1 times z minus a whole power m fz. That will be the for z equal to a, if it is a multiple pole. The third one is if fz is of the form pz by qz, some function, of course qz should be different from 0, and then the residue can be calculated at z equal to a can be calculated as a limit z tending to a by pz by the derivative of qz, of course z tending to a, or simply we can write down like this, pa by the derivative at a. These are the three important remarks which we have. Now the first example what I want to do is a simple example I want to evaluate is fz is equal to z by z minus 1. So I want to evaluate the residue of this. So the zeros of fz is z minus 1 0 implies z equal to 1. So z equal to 1 is a simple pole. I say it's a simple pole. Now I have another example of fz is, I would like to evaluate a function like z by e power z minus 1. Evaluate the residue or whatever it may be. Let us see a question in a different way. Discuss the nature. Discuss the nature of this function fz. Let me see. So the zeros of fz are e power z minus 1 equal to 0. This implies e power z is equal to 1, implies for 1 I can write down e power 2n pi I, where n belongs to z, set of integers. Clearly n equal to 0, if I substitute n equal to 0, it is e power 0, which is 1, n equal to 0, then z equal to 0 is a simple pole. Also, let us see the fz as z by e power z minus 1 is equal to z by e power z is this, the expansion of e power z is 1 plus z square by factorial 2 and so on minus 1. So I can cancel this plus 1 and minus 1 and I will write down z by, now I want to take z common, so z into 1 plus z by factorial 2 plus z square by factorial 3 and so on Again, I can cancel this z. So look at the limit. The limit of z by e power z minus 1. I am looking at the limit of the function z tending to 1. If I put n equal to 0, this is e power 0, so z is 0. So I will write down limit z tending to 0, z by e power z minus 1, which is limit z tending to 0. What is e power z minus 1? It's 1 by, already I have calculated, z by e power z minus 1 is 1 plus z by factorial 2 plus z square by factorial 3 and so on. Of course, I have already cancelled z, assuming that z is non-zero. So z is tending to 0, but it's not 0, remember. So this will be 1, which is finite. The limit exists, limit of the function exists, hence z equal to 0 is a removable singularity. It's a removable singularity. And also z equal to 0 is a simple pole. So it's a removable singularity, but when I am talking about the pole, I need an essential singularity. Anyhow, I will stop the story here. Removable singularity is simply, I am assuming this. What about if n is different from 0? So limit z tending to 2n pi I, look at n is different from 0, n is 0, case is dealt. Already I am looking at n equal to 0. If n is 0, this is. In the same fashion, I will get 1 by 1 plus z by factorial 2 and so on, z square by factorial 3 and so on. Z tending to 2n pi I, n is, now this goes to infinity. Actually, I don't want to write infinity. This is actually, we write plus infinity, but usually this limit is equal to infinity, or if this tends to, as n is larger and larger, this goes to infinity. Thus, all are simple poles. What are all? Those all are n different from 0. That is, if I put n equal to 1, it's 2 pi I, n equal to 2, 4 pi I, n equal to 3, 6 pi I, and so on. But if I have a choice of n taking a negative integer also, so plus or minus, plus or minus, plus. So there are infinite number of simple poles for this example.